All right, so in this video, we're going to be looking at an application of some of the algebra that we've been learning, in this case, the distance formula. And what we're going to be doing is we're going to be creating a function that is going to express the distance between a function and a point in space. Now, the way that we're going to do this basically is we are going to have a generic point on our function, xy, and we're going to calculate the distance to this fixed point in space. So the first thing that we're going to do is we're going to take our distance equation, and we're going to have x minus 2 squared and y minus 5 squared. Now, because this is a specific function and not just some generic point in space, we do have a way of expressing y in terms of x. And so we're going to replace y in our expression with the x coordinate. The function that we're using for this example is x squared minus 2x minus 3. And so that's going to go in this expression down here, x squared minus 2x minus 3 minus 5 squared. And then we're going to simplify x minus 2 squared and x squared minus 2x minus 8 squared. Now, in order to simplify this any further, we're going to need to FOIL everything out. So now, one thing that's very important to keep in mind is you cannot distribute powers. You have to actually FOIL. For the first part, you can use the perfect square trinomial formula from the squaring of a binomial. But for the second component, we are going to have to just FOIL. So I'm just going to FOIL both of them. So x times x is x squared. X times negative 2x. Negative 2 is negative 2x. Negative 2 times x is also negative 2x. Negative 2 times negative 2 is positive 4. And then x squared times x squared is x to the 4th. And then x squared times negative 2x is negative 2x cubed. And then x squared times negative 8 is negative 8x squared. And then I go on to negative 2. Negative 2 times x squared is negative 2x cubed. Negative 2x times negative 2x is positive 4x squared. Negative 2x times negative 8 is 16x. And then I multiply negative 8 by everything in the second parentheses, negative 8x squared. Negative 8 times negative 2x is 16x. And then negative 8 times negative 8 is 64. And now I have to combine like terms. So my highest power is x to the 4th. I have 2x cubed terms, negative 4x cubed. X squareds, I have negative 8x squared, and negative 8x squared is negative 16x squared, plus 4x squared is negative 12x squared, plus one more x squared is going to be negative 11x squared. And then how many x's do I have? I have negative 4x here. And then also two 16x's, so that will be 32x. 32 minus 4 is going to be plus 28x. And then I have a constant of 4 and a constant of 64, and so it's going to be plus 68. Now, this is my expression for the distance between the points. So for each value of x. So let's go back to our graph. Let's say I'm at this point here. This is going to calculate when x is equal to 1, what the distance is between this point here at 1, -6 and the 0.25. But if I'm over here, let's say at -2, 3, then it's going to calculate the distance between the point -2, 3 and 2, 5. So just by plugging in the x coordinate, it's going to tell me what that distance is. And you can imagine this parabola going on forever. And what it's going to do is there's going to be some point where there's some local minima. There's going to be a sort of local maxima. And then there's going to be, the graph is going to go off to infinity. Because once you get past this point on this graph, then it's just going to get further and further away. Now let's take our function and graph it to identify what those local mins and maxes are. Now, if we go ahead and graph this function, we end up with this. And so I've used Desmos to also plot the minima and maxima here. So recall from our original graph, it got close, then it got further away as it went toward the vertex, and then it got closer again. And then it, again, on both ends, it eventually went off to infinity. So that is consistent with our expectations from our previous graph. The minimum distance to our 0.25 is going to be the value 1.97 approximately, and is going to occur at the x value 3.94. Again, approximately, because this is a decimal. So that's the absolute minimum distance. The closest point that you can get to is when x is about 3.94. When the next closest point, so a local minimum is going to be, again, as the graph, we saw this from our original plot, oops, too far, that you're here, so somewhere around here, you're as close as you can possibly get. There's another point over here, which is also going to be closer than other nearby values, not as close as you can get over here, but closer than you can get on this side of the graph. That's going to be this other local minimum. So that's going to be here. The distance will be 3.94, but the x coordinate where that happens is going to be -1.885, etc. Now, the maximum, the local maximum, so where it's going to be as far away as it possibly can be as it goes around that bottom of the vertex, is going to be when x is equal to 0.94. That distance there will be 9.5. But as you saw, on either end of the parabola, this is eventually going to exceed that maximum and is going to run away, getting further and further away as much as possible. So these are our local max and minima. And if we were trying to describe increasing, decreasing functions, these minima and maximum values would then become the endpoints of our intervals. It's decreasing until it gets to this x coordinate, then it's increasing until it gets to this x coordinate, and then it's decreasing until it gets to this x coordinate, and then it's increasing again. For a function like this, it's very difficult to get the perfect combination of parabola and point so that these numbers come out to be nice whole numbers. So approximating the endpoints is fine.